Good morning. Let us continue with the topic of nucleation. So, we arrived at an expression for the nucleation rate from a three factor model. We can identify the factors right here. You have some factor dealing with the number of equilibrium critical clusters which will exist at any temperature, which is the key term, because of which that second term in the exponential with the negative sign comes, which is the key term there. Then the prefactors which basically account for the collision rates, and then Zeldovich factor, which is the non-return probability coefficient. So, I think Rochish asked me the one question about a S being there. Actually, if you go back to an equilibrium, that 1 by S there is artificial because it is multiplied by C1, which is proportional to supersaturation. So, that S cancels. So, this S comes from the collision rate S, which is proportional to P1. So, that is why it stands there. So, it is correct. In fact, that is why the flaw in some papers where it was S square or something used to come earlier, because they were not doing that e to the power minus correction which is done for continuity with respect to mass action law. So, which is now the correct standing formula. But all said and done, as I mentioned, the entire pre-exponential term is treated as a prefactor in many theories, and only the free energy delta G by kT is treated as the key nucleation factor, more like an Arrhenius relation. It comes to an Arrhenius type relation. So, if you estimate A turns out to be very large, A is very large, almost totally offset by the very small value of e to the power minus NC by 2 ln S square, unless S becomes substantially high. And that is the point which we have illustrated in this right hand side graph. Let me, does it show here? This arrow? No, can't show. But anyway, we can see here that typically it is said that we say that nucleation is observable if there is a formation rate of 1 particle per cc per second, which is about a million particles per meter cube per second. So, if that is the number, we say it is above or it is nucleable. If it is less, then it is nearly not possible to detect. That is why that red line is drawn there, and you can see that the transition occurs as we cool down the liquid. This is one way of achieving supersaturation. So, that is the exercise that is done here for water, starting with some given amount of water vapor. So, want to terminate this chapter of homogeneous nucleation here, because there are lots of theories which still go or which are being tested or have been tested in the near past. So, subject is a very live subject, keeps repeating again and again many questions. I just want to briefly touch upon a few points of limitations, right, before I go to something else. So, we have limitations which we have been discussing from time to time. So, the kind of theory that we have presented still works only for limited liquids, and that too in limited temperature change. It may work for one liquid in one temperature change range and may not work elsewhere. So, most of the aerosol based validity has been for water, or of course, because that is the most important thing, and then there have been tests with other alcoholic liquids and all. Some experiments have been done to validate it in some way, but by and large most of the limitations have been of the theoretical nature, as we mentioned, and also the fact that we are assuming quantities like surface tension, the liquid density down to nanoclusters. One major limitation. So, that is where the problem comes, that where do these begin to manifest, at what size is a question to be asked. One molecule does not have surface tension, obviously, unlikely the dimer will have. So, then we do not know where to. So, surface effects become important, finite size effects. So, that is one major limitation. Then we did not discuss the temperature dependence of these quantities, which is another. So, these are some of the limitations.
I have one small doubt. One is, of course, about the whole continuous phase being either vapor or liquid. That is one aspect. If you are looking at condensation versus dissolution, crystallization versus condensation, the continuous phase being air or liquid has not much bearing on the
Homogeneous theory does not seem to worry. Yeah, but the difference comes about the concept of supersaturation. There you have solubility as the equivalent criterion. So, all the complexity of solubility enters there. Here supersaturation, host gas is a bystander. It does not have much role to play. Whereas, when it comes to solubility, the solvent solute interaction has a serious role to play. So, that has to be separately accounted for. Once you do that, nucleation formulas are more or less same, because I have used for crystallization also same nucleation theory, accounting for the effect of solubility being dependent on temperature as well as solvent properties. That is the difference.
And then another issue is, suppose you are looking at just vapor, pure water vapor condensing out, versus water vapor in air condensing out. Then, as you just mentioned, that if it is a monomer, there is no interfacial tension. But if air is the medium in which vapor is condensing out, even the monomer will suffer.
Yeah, but air is the host gas we take as almost inert, totally non-participatory. Much like that famous question we ask, if you have a beaker in which you keep water and here you have air and there is another beaker, same temperature T, but here you have argon, and third one you can say it is vacuum. The vapor pressure, so called P infinity, will they be same or different? This is argon, vacuum and air. So, the answer is that it should be the same, because vapor pressure is a function only of temperature, not of the host gas, assuming that they are all inert. So, the Torricelli vacuum vapor pressure of water above that is exactly the same as the normal vapor pressure we would have at the same temperature.
But my worry only was with surface tension, because surface tension, even if a tiny water droplet is formed,
does it really? Yeah, but does the surface tension depend so much on the density of air? I do not think. In vacuum also, water will have almost 70 to.
But if it is pure water vapor, if pure water vapor is condensing, then it's not, it's water, both the components are water.
Okay.
So, sigma in that case is the interfacial tension with its own vapor.
Yeah, but that is what I said. The so called interfacial tension, liquid and vapor, is same as that in vacuum. In vacuum, it does not make much difference. Order, because of 10 to the power 3 difference in densities, mainly because number of molecules which will be pulling it upwards is not negligible. So, typically it is taken only as sigma. Here it is a vacuum. I think that I think is done. Yeah. So, with this thoughts of basically limitations, let us see how people have, what kind of methods are used for experimental validating. We will not go into the details, but we should know this is also a parallel subject which goes on. So, often the tool used follows closely the assumptions we make in nucleation theory. So, it is basically called as thermal diffusion cloud chamber is the kind of system that is used. It is basically a cloud chamber. So, here you, as the picture shows basically I have a chamber in which there is an upper and a lower plate, it is fully closed, and you keep different temperatures and you try to maintain different vapor pressures. You have, I think, source of vapor is coming from here, and you adjust the pressure differential also, I mean the pressure means vapor pressure differential along this, and also a temperature difference. So, it is a bit subtle thing how that is done. Temperature is okay, we know how to maintain it, but simultaneously a P differential also gets set in, but you choose such a combination that the pressure also decreases, but the temperature decrease is stronger. So, that is the way we see that temperature should decrease little stronger, so that overall the equilibrium vapor pressure, equilibrium vapor pressure should be less than the maintained pressure, and that is not parallel. So, you can see that they are not parallel. So, there is a point where there is a maximum P by Ps. So, which means that is where the tendency, the driving tendency should be the highest. So, as a result of which, somewhere along this line you start getting a rain burst of nucleation. There are good videos available how this operates, and in fact, it happens periodically in experiments, because once nucleation takes place, it reduces the vapor pressure, again the whole nucleation stops, then after some time it again builds up. So, lots of rain out type of videos are available. So, you then once the nucleation process sort of starts, and then you have so here is a P by Ps ratio, and then you have a burst of nucleation taking place at a certain level, which is then viewed through a experimental setup, either by light scattering. Which should be parallel? J, right? Well, I think they have shown it just where the S becomes peaking. See, S you can see the peak, right, at some height. So, most of the dominant is 1 by log S square term. So, that is where you will have the sudden burst and the peaking taking place. So, this is the way they sort of measure.
The PS is a function only of T.
Yeah, PS is a function of T. So, you do not have a direct control, but by adjusting temperature and S, the nonlinear curve can be made to give rise to this kind of S-shaped curve. That is how it is done. Yeah. So, there are a lot of details in it. Those who are interested can definitely look at this, and unfortunately, I do not think there is any diffusion cloud chamber built here. I had seen one I was in Germany, but not many groups must be working on this kind of experimentation. Yeah, cloud chamber has many applications. So, this is an adaptation to study the nucleation phenomena, not just homogeneous, any nucleation phenomena you can study now. So, it has a lot of environmental atmospheric applications, how aerosols affect and all that. Yeah, this is supposed to be some relatively recent, it is already 30 years old, but compared to the early 1950 and 60s experiments, is a relatively later, and it is done for butanol, and the homogeneous nucleation rate estimated by the model is supposed to have agreed fairly well with some of the experiments done by this group led by Vissanen et al. And you can see that is a log graph. So, even a small disagreement would be in orders of 10 and all that, but that is sort of understood or accepted within the framework of the nucleation theory. There are some other experiments which I am aware, which I am not showing here, where the experiments were specifically done to test not between the two classical theories, but between the classical nucleation theory and another theory called Lotte-Pound theory. It is a statistical mechanical theory called replacement partition function theory or something, and it was a big challenge which was questioning the thermodynamic basis of the whole thing, and this were going by statistical mechanics via partition function methods. They had a very fine argument that the problem is it is not sufficient to consider the vapor phase. When we say a crystal in a liquid drop in a vacuum is not the same as a liquid drop inside a water. because moment it is in a water, it has all orientational distributions will come into picture. So, that also has to be accounted for. So, that was their theory, and there were a lot of controversies, but somehow experiments are supposed to have discounted that theory. There were orders of magnitude difference, and so today I do not hear anyone talking of Lothé-Pound theory as such, but the challenge they raised is a question which I do not think has been answered, because their mathematics and the logical methodology follows statistical mechanics in its full glory. So, but then I am not very sure if my literature knowledge is good as of now. People must have discussed this much more, but generally these formulas are not used for aerosol nucleation. Yeah, so with this we now come to another part of particle formation in aerosols, and that is called as the heterogeneous nucleation. As we mentioned that it is by the presence of particles that most of the times we get visible particles being formed rather than by homogeneous nucleation. Understanding this phenomena of heterogeneous nucleation, however, follows what we have studied so far. So, homogeneous nucleation is important as a framework for understanding every other type of nucleation. So, as I mentioned, heterogeneous nucleation has two parts. To understand heterogeneous nucleation, we must pay attention to the role of a foreign surface in inducing a cluster from a vapor phase. So, the picture we have in mind is a ideal clean surface. Let us begin with the flat surface, and I have condensable vapors here. And I want to know under what thermodynamic conditions will some visible centers be formed here, which will then grow and form a continuous phase and remove the vapor from the atmospheric phase. So, this is basically foreign surface assisted nucleation or surface mediated nucleation or simply heterogeneous nucleation. The most important aspect that we have to pay attention when we are talking of this type of system is the role that interfacial tension begins to play. So, for a pure liquid we were talking of only a surface tension, and as you would have heard between me and Rochesh the discussion, the so called surface tension was actually the interfacial tension between the liquid surface and its own vapor, which is taken roughly as the same as that between the liquid and a vacuum. Ideally you cannot have a pure vacuum, but imagine you have. However, moment we have a surface and we have a liquid, then there is the interplay of the adhesive forces of the solid and the solid liquid, and a greater affinity of the solid, a certain affinity of the solid to the liquid would reduce either of them. Their individual surface energy densities would be sort of compensated in a way. The forces would be compensated because some molecules are now available for each of them to compensate for the absence of those molecules or voidance of this molecule. So, that is the concept. So, we accordingly, when we have this picture, we postulate three, we call them as surface tension or three capillary constants. One is of course LV, which is the same as sigma. This is the liquid and vapor. Which we already have discussed. In addition, we assign certain surface free energy density. Sigma can be actually referred to as surface energy density, right, per unit area. Call it as a surface tension and some kind of an adhesive energy, which we call it as sigma SV, because vapor is here. Let us say it exists, and then accordingly this is solid vapor. Then we have an interfacial density, interfacial energy density or interfacial surface tension, which is solid liquid. We presuppose the existence of these constants. These are system constants, more like that they exist. So, energy, therefore, associated energies will always be, you multiply by the surface area, you get the energy. So, when energy is a quantity which you can always balance, add, subtract, so you work with those. That is one way. Second way is also forces, they still will be used, and you must remember the concept of a force in the case of a surface tension. So, if I have a liquid surface, so this is a liquid surface, then we define surface tension as a force per unit length of a line that we put on the surface. You must be able to visualize that if this is my surface and there is a tension on the surface, then if you put a thread, every element of the thread faces a certain force. So, surface tension, that is why has the dimension also of Newton per meter. So, it is force per unit length. So, in many times it is useful to do force balancing, like why does my pendant drop not fall, its weight is balanced by this force. So, that concept also is useful. So, with this definitions, before we go into nucleation per se, we must understand the stability of a drop if it is formed, because all these energy differences which cause the driving forces require us to understand the occurrence of equilibrium if they existed in their independent states. That is the idea. So, when we keep a liquid on a solid surface, then it is known that the liquid does not spread spontaneously. On certain surfaces, liquid almost remains a sphere, they are super hydrophobic. So, we are quite aware of these surfaces, super hydrophobic surfaces. So, traditionally, if you remember, lot of our literature is based on lotus leaf, because that is a super hydrophobic surface which does not contact, water does not contact, and it remains uncontaminated by water. So, that is the way it is given. So, this is a surface where it does not spread. Similarly, or hydrophobic in general, super hydrophobic is the extreme case used for keeping it perfect spheres, but in typically hydrophobic. And we have hydrophilic surfaces, which are also called wetting or wettable surfaces. So, more hydrophilic it is, more it wets, and more it wets, more it spreads around. So, between these extremes there are a large possibilities, the one where it completely wets and the where it does not wet at all. So, what brings the difference between these two extremes? So, that is where we speak of so called angle of contact. So, to visualize, angle of contact is always defined in this kind of convention from a positive x, if this were x axis, measured along this direction of a drop, taken on the hind side of the drop. So, the angle subtended by the tangent to the surface at the contact line. So, based on this perspective, the hydrophobic will be a situation where a droplet remains as a sphere let us say ideally, perfect sphere, right. So, what will be the angle of contact if I have to measure this way? The tangent line would be something like this, let us say almost, right. So, it will be very close to 180 degrees. So, angle of contact equal to pi is what characterizes a superhydrophobic surface. Similarly, for a hydrophilic surface, it spreads so much. So, my angle of contact theta is likely to be 0, very small, 0. So, theta equal to 0 defines the angle of contact for a hydrophilic surface. So, there could be a pi by 2 situation and all that. So, you can now think of a hemispherical drop here for example, then the angle of contact is pi by 2, that is a hemispherical drop. So, we can have various situations. Now, with this knowledge, let us try to relate this angle of contact to the various surface tensions that we have postulated. It is a very simple way of deriving it is what I am showing here. So, if I take now my drop, let us keep it like this, and if this is my, so what will be, and surface tension has to be drawn as a tangent to the surface at the line of contact. So, this is my line, there is a line of contact which is a circle, hemispherical drop will actually form a circle here, right, my drop is placed on that. So, every point there is a tension. So, this is nothing but sigma L vapor. So, there are always some vapor molecules and host gas is inert. So, I merely assume its presence in the background. So, we call it a sigma LV, and that is the one which is the normal surface tension, we call it as the angle of contact. And given the other two definitions, we have sigma SL. At this point liquid is in this direction. So, it will be a kind of a force, it will induce proportional to sigma S solid liquid into the liquid exactly at the interface acting at the line of contact. Now, entire bulk solid which is here has some surface energy equivalent of a surface tension, and we call it a sigma SV, because there is no solid above it. So, tension will be there, and that is associated as sigma SV, and if associate a force accordingly along the same surface. So, treat each of them as force, because per unit length it is. So, on a length of the contact line it will be a force. dl if you take, it will be a force, and hence forces have to balance if my drop has to be stable. So, treat surface tension directions as forces, and there must be a force balance. Force balance horizontally. I do not want to talk vertically, because that pressure surface it will be normal reactions and all will take care of that, we hope that. So, force balance horizontal. So, the force in this direction sigma SV going outward toward the solid side, that should balance the force that already acting between the solid and the liquid sigma SL plus a component of the surface tension force taken on the line of surface, taken on the direction of surface, which is sigma LV cos theta. I am sure many of you would have studied it at some level or the other, but it is important that we understand this again. So, that immediately we get a formula cos theta equal to sigma SV minus sigma SL divided by sigma LV. This is called the Young's equation. So, it connects the angle of contact to the three surface tensions that we postulated. So, as I mentioned, so when do we get hydrophilic? So, hydrophilic is when theta gets closer and closer to 1. So, when the you can see from the ratio, or you can take it back here, you can work along this side, that when theta becomes 0, then cos theta is 1. So, basically sigma SV should be equal to sigma SL plus sigma LV ideally, but if it is even more than that, cos theta will be more than 1, which is not possible. So, it will remain at theta equal to 0 only. So, that is why when sigma SV is much greater than, which means it is basically greater than or equal to sigma SL plus sigma LV. That is, when the solid tends to be adhesive to itself over dominantly as compared to the whatever liquid the cohesive forces are there, then that leads to a case of theta equal to 0, more like hydrophilicity. That is the meaning. The contrary case of a hydrophobicity exactly is when the liquid cohesiveness is stronger than the solid adhesiveness. That is, the liquid tends to envelop itself into a sphere, it is not compensated by the surface activity of the solid. So, then it remains as hydrophobic, in the sense it remains as a sphere basically, which is like saying that the liquid cohesiveness sigma SL is greater than sigma SV. So, that is the other case. This is theta equal to 0, and the other one is when sigma SL is much greater than the sigma SV plus sigma LV, then we say it is more like theta equal to pi. So, physically that is how we remember. Solid has a greater tendency to be with itself, or the liquid has a greater tendency to be with itself. These are the two extreme cases. So, with this we can now go to our problem of heterogeneous nucleation. That is what we will do now. Okay. We have this formula, right. So, now let us get into the question of the free energy of this spherical cap. We are discussing a spherical cap on a surface. Armed with this definition, I have this spherical cap of a liquid having a certain contact angle theta, and there are vapors all around it. This solid, smooth, uncontaminated solids, all these niceties have to be brought in, which are so unrealistic, but that is, we have to postulate that. So, now we to be able to get an equivalent of a free energy term, first thing of course we have to complete this sphere. We again see, we make an assumption that it is a part of a spherical cap. There is no reason why it should be spherical. You can ask a question why it is not a parabolic shape, why it is not any other concave shape. Everything is possible, but theoreticians, you can argue, you can work out very nicely that some area minimization will occur, and that naturally will lead to a spherical equivalent shape. So, with that I construct a hypothetical radius r and a center here, and I consider my volume of the drop as V. So, V is the volume of the drop, which is same as the number of molecules in the drop. Same means multiplied by molecular volume. You have defined what a molecular volume is, right. So, they are one-to-one correspondence. We can relate my V to R by pure geometry, right? Because if I now have an R, then the total, my volume V is nothing but the total volume of a spherical cap, a conical spherical cap, minus that of the cone itself. So, subtract the two volumes, it is a geometry, and we tend to get that relationship here, the volume as you can write like this, V equal to, it comes to 1/3 pi r cube into 1 minus m, yeah, I will tell you what m is, 2 plus m, where the convention is m equal to cos theta. We use that definition because now it is a number. Only thing we should remember is if m is cos theta, then theta equal to 0, what is m? 1. When theta equal to pi by 2, 0. And when theta is pi, theta can vary from 0 to pi, right, upper side. So, this will be minus 1. So, that is why one likes m, because it is symmetrically distributed now. It maps from theta to pi to minus 1 to 1. So, with that you can relate the volume of the spherical cap to its radius. Since volume is the quantity I will be giving, which is and angle of contact is fixed by the property of the liquid and solid, it does not change. So, my R therefore can be written as some A m into V to the power 1/3. Here also we can write, because I can take R 1/3, if I take R is equal to V by this, and where my A m is just the these coefficients that we have introduced, that is, this is just a notation, A m equal to 3 by 4 pi into all this. One-third. Sometimes you will see people writing it as expanded form, some 1 minus 3 m plus m square or m cube or something comes. So, when you expand this whole thing, there is a square here and 1 m, so m cube will be the highest term. So, both are factorizable like this. Now I do not use the force concept, I go to the energy concept, because when you have to minimize, we are talking of energies. So, there are, how many energies will be there? How many energies I have to consider? One, I will hint. So, one surface energy is the usual surface energy, right? Then what other energies do we have to add or subtract? Yeah. So, we have an energy associated with this surface, which is pi into some h square or whatever, and we have to subtract the energy that was there in the solid before the liquid was there. That is the change, right? There was an energy on the surface, which is infinity of course, but let us say large energy, whatever. But by placing a droplet and introducing the interfacial tension, we have changed that energy. So, that will be the free energy change that we have brought out by placing a drop on a solid surface. So, we have three surface areas have to be first calculated. One is area of the cap, which I call it as ALV. This is the area of the cap. So, then we have similarly area of base, that is ASL. These are the two areas, and we can calculate the corresponding values, like ALV is 2 pi r square into 1 minus m, is a pure geometry. So, we can always do that, and remember my r is now replaceable with v. So, So, same as my volume of the drop. So, we work with R, it is easier, and similarly this is pi r square 1 minus m square. So, you get these areas. So, the energy is nothing but straight away I write the expression for the change in free energy delta G will be equal to sigma A LV. Sigma means sigma LV. I am just keeping it as sigma. Here this is sigma LV, we take it as just sigma, just as a notation, which is very close to the bulk liquid surface tension. So, sigma A LV, then the change that is brought about because of the sigma SL minus sigma SV into area of that circle minus the thermodynamic quantity of having to assemble n of these monomers on this drop. Here I said there are V is equivalent to some n monomers. So, we have already calculated from thermodynamics that to assemble n monomers we need to give energy of kT log S by VL, because V by VL is n. Right. Earlier it was the n kT log S, remember.
So the sigma 4 pi r square got replaced with
That's all. Exactly. That's right. And here I have assumed the existence of a supersaturation, which I did not mention, but I should have done that. So, my supersaturation is the maintained concentration by that required by equilibrium considerations for a flat liquid surface. So, supersaturation is understood as defined. It is always P by P infinity, maintained by that over a flat liquid surface. Value of A. You are not able to read? It is no, sorry, minus 1 by 3 होना चाहिए ना? नहीं. Oh, 3 by pi. Yeah. I must have done that. Yeah, mistakes are there. Right. That actually does not have much role to play, but one should know that correctly, yes. Yeah. So, now you can express it very directly. So, it all comes to minus of pi by 3, you have to substitute all the quantities, 1 minus m whole square into 2 plus m kT ln(s) by VL, r cube term will be there, minus 3 sigma r square term will be there. So, the reason why we went for R is it nicely factorizes out the angle dependent part from the variable part. Now, this sigma g, which is a function of m as well as r, and we say that my m cannot be a varying quantity, it is fixed by the property. Hence, the minimization nature will accept via minimization with respect to r. It is a hidden assumption that we have to make. So, as usual, I say what is my critical size r at which this becomes 0. Let us say at r equal to r star equal to 0. So, when you do that, you get an expression exactly as we got, that is R star equal to 2 sigma VL by KT lns. Exactly like Kelvin radius for a sphere as far as R is concerned. But R is a hypothetical quantity here, right? It is not the real volume of the liquid. So, the difference comes from that. Number of molecules assembled are much different from that assembled by a sphere of radius R. So, but the radius of curvature apparently remains the same for this. So, with that we now substitute back. This is the quantity, is not a fundamental quantity of interest, it is an intermediary because it is hypothetical. So, it is an intermediary derivative, but you substitute this R back here and you will get delta G star, which is the quantity of interest. So, with that we can show after substitution that my free energy per kT takes up the form, I call it as delta G star hetero by kT is going to be U 4 pi by 3 VL square sigma by KT whole cube 1 minus m square into 2 plus m. Maybe I can. Right. Now, we should remember the result we obtained for homogeneous case. For the homogeneous case, the corresponding free energy barrier, free energy for at the critical, the barrier height, yes, at R equal to R star, that is why they starred here, that was 16 by 3 VL square, again sigma by KT whole cube. Can refer back to our notes and we would see this. We can write in terms of NC and all that we have done. Right. Yeah. I am just wondering whether I missed log s cube term, log s square term, let us see. What's stuck up?
Even in hetero it should be there.
Yeah, it will be there. I mean, I just a slip if at all, because it does not matter. We are going to discuss the free energy term ratios. Log s term should be there. 1 by log s square was always there. It would come because when you do that, this will dominate. R star is 1 by log s is there. So, 1 by log s square should come. Maybe I just took down the notes hurriedly, and here I am not discussing those things. So, yeah, maybe here also I missed it. I will correct it later, but right now let us say it is there. So, the point of interest is the so called ratio, barrier reduction by virtue of having a surface for nucleating now. So, that barrier reduction, by the way, we can now check that these two are consistent, because if you put m equal to -1, it is a completely hydrophobic surface, then it is a sphere. So, if you put m equal to -1, this is 1, this becomes 1 plus 1, 2 square is 4, 4 into 4 is 16, you get the same thing. So, I was paying attention to this quantity, so I missed the log s in my notes, but it will be there. But I will confirm it. I mean, if there is something somewhere else it is absorbed, I do not see it, but it must be like this. But the point is that m equal to -1, it agrees. So, the ratio delta G star by kT, see, in any case log s will cancel, that is why it does not matter. For hetero is often written as delta G by kT, for homo multiplied by a modifier, a free energy modifier function Fm, where that free energy modifier function Fm, free energy modifier due to foreign surface will be 1/4 of 1 minus m whole square into 2 plus m. It is purely dependent on the angle of contact. That is why this theory is so attractive. In spite of all the assumptions we have made, it at least gives you a formula for a quick check how effective is my surface in facilitating, no, what, right. You can write in terms of theta as I have done here. So, as that figure shows, for theta equal to 0, f0 is 1. So, it is a completely wettable case. So, sorry, f0 is 0. So, this for a perfectly wettable surface, f0 is 0, which means free energy required to form the critical drop is 0, which means barrier is completely brought down if you have a theoretically very ideal spreading surface, and instantly a nucleation will take place regardless of S value. Moment S greater than 1, of course, log S is there, so it must be greater than 1, instantly you will have surface condensation taking place. Exactly the opposite when M is for theta equal to phi, f pi is 1. So, as a result it goes back to our homogeneous nucleation theory. I mean, at least the barrier height. I do not say homogeneous nucleation theory for the rate, but the free energy barrier will be the same as that of a homogeneous nucleation. This variation is a smooth function as is shown there. So, if it goes to 1 for theta should be 0 to pi, right. So, it must reach 1 at pi like this. That is how it should reach. Now, we get an idea, basically theory is not complete, but we get an idea that foreign surface lowers the barrier, and the extent of lowering can be estimated via free energy reduction. Now, when you talk of nucleation rate J, the concepts themselves differ, because J was defined as number of nuclei formed per unit volume per second. So, on a surface it should be now number per meter square per second. So, if I have this surface, how many such droplets will be formed? As we always see, when something condenses on the glass, beginning you will see some tiny droplets on the surface, large number. Now, the whole concept of equilibrium cluster distribution is not much attempted. The reason being that in any practical problems dealing with surfaces, what matters is the surface character itself. There are patches where this sigma vary wildly. A little contamination on a surface changes the surface tension widely. It is well known experience. You can do these experiments in our own CL610, I think is next, right? Experimental methods. Yeah, these some studies you can do, you contaminate and you see a very different surface tension. As a result of which, often it is presumed that there are only certain sites which are nucleable, that dominates. So, normally one assumes a site density number per centimeter square or meter square and then multiplies by the flux, beta flux that we mentioned, and gets a rate. So, that is how it is normally done. To give you an idea, I think these numbers can vary widely, even site density. What exactly is the site density? So, mostly it is these patches of contamination, cracks in the surface, micro cracks on the surfaces which act as nucleating centers, and if theoretically you want, it must be something like 1 by pi r star square itself as being the number that is maximum possible. So, this is the kind of debates which go on there. To give you an idea of contact angles, as I mentioned, these numbers, it's all internet numbers, but you can check, it's more or less correct. If it is a clean water and glass, it's about 30 degrees is considered. Teflon is 110 degrees, and it seems glass and coconut oil is 9 degrees. It's very highly wettable. That's why it's so difficult to clean these oils from surfaces. So, now I remember, and why it is so nutritious for pests, they thrive on coconut oil because it's always sticky on surfaces. So, its contact angle is low, which has a major role to play. So, here this is
that the reason that normally you would seed with the same particle. Suppose I want to crystallize on sugar, then my seeding will also be so that the sugar crystals.
Yeah.
The contact angle.
Yeah, I am coming to that. In aerosols, same thing is done by heterogeneous nucleation on spheres. So, this is the starting point. In reality, nobody uses flat surface in aerosols. You have to go for spheres. We will just briefly discuss, but that is exactly a point. It is true in liquid also, a foreign surface mediated growth, but it is not nucleation per se, it is growth of that particular particle. So, numbers will remain the same as the original ones, but they will grow. Yeah, so you can see how the delta G by kT is brought down drastically for a certain is water, an ideal surface with various contact angles. The original delta G by kT for pure water is about 165. If you see some of old calculations, it is 165 times higher than the thermal temperature, the free energy is, but it is brought down to of the order of 1 and even less than kT. So, almost a barrierless bringing down has occurred. Now, actual realization, as I mentioned, requires that prefactor, because ultimately J is some prefactor into e to the power minus delta G star by kT. See, that is how in a simplified formula you can have for nucleation, and this will include the number of nucleating sites per centimeter square into some attack rate beta, that is the condensation rate, and you will get this kind of a formula roughly. So, these numbers can vary from 10 to the power 6 to 10 to the power 19, this is what I heard, per centimeter square, these numbers per second. So, this has given us a rough idea of how foreign surfaces basically mediate and help us to reduce the so called nucleation barrier. That is a lesson from this analysis. As I mentioned, in reality, in atmospheric aerosols, the quantity or the particles in the atmosphere, they act as the foreign surfaces. And if you look at our atmosphere, we have large number of what are called as CCN, cloud condensation nuclei, right? Cloud condensation nuclei. They are also called as Aitken nuclei. He is the scientist, I hope it is Aitken, I have to check this, must be E, Aitken nuclei. So, the scientists who brought attention to these small particles, like in a clean outdoor atmosphere, your typically 1000 particles per cc is common. They are all in the Eichen mode. Your OPC counter will not detect it, but they exist in condensation counter will detect it. You will get about 1000 particles per cc when you measure, which means 10 to the power 9 per meter cube when you measure in the atmosphere, and they are required for forming the clouds eventually, all this. It has been sustained, and the whole question of climate impact of anthropogenic aerosols, one of the important questions is how rains are going to be affected by the foreign particles we are putting. And you may think that more particles you put, it is good, you will have more rains, but it does not work out that way, because they make everyone poorer by not having enough water vapor. So, that is not conducible for rain. Droplets do not grow, you see clouds, but none of them will rain. So, there is a certain optimum balance required for the critical nucleus to exist in the atmosphere, and that is why there is a serious concern on the role of anthropogenic aerosols on this so called one of the direct effects of climate change, rain formation. Anyway, that is a background why these topics are important. However, the
Salt aerosol.
yeah,
They are natural aerosols.
I am going systematically. That comes in hygroscopic growth, another aspect.
But atmospheric CCNs are like
Hygroscopic, they are better, they are much better, sea salt and all that. So, nature has been providing it quite often, but that can have a role. Yeah, again it will grow, but it may not rain out. There is an optimization required because the water vapor is limited. So, they will divide among themselves, but they will be too small to settle by gravity and will not come down. That option, that problems are there. So, anyway, that brings in the importance of understanding heterogeneous nucleation, but the subject is not really very well developed. Here I just give you a one slide presentation I am making here to you, just to see that all that we did for the flat surface conceptually has to be now modified to include a finiteness of my aerosol particle, which I assume as a smooth surface, which I assume to have a contact angle theta with, if it was a flat thing, a certain contact angle on a certain embryo that would be trying to get formed on it. So, this is my embryo which is trying to nucleate on that surface, and the total surface area of all the m particles, it is equiprobable, any on it can happen. So, I can count the total surface area in the atmosphere as being responsible for the overall effect of heterogeneous nucleation. So, the theoretical concepts will not get into the maths of this, it is just geometry basically. Same way you do energy you construct, postulate the 3 surface tensions, you do it for the fact that my base also is a curved surface now. So, it is a complex geometry problem. Surprisingly, this was done as late as 1960s, not very long ago. Yeah, but this is one paper that is first did it. So, you get a, instead of that modifier function is the only thing that changes. So, delta G star by kT has now another modifier function, which is not only a function of the contact angle m, but also of the ratio of the particle diameter to the r star critical radius also plays a role, and into delta G star by kT homogeneous. This is hetero. The hetero and the homogeneous rate free energies are related via a modifier function. No point in writing down that function because it is quite longish, it is there in the things, and but all that you should remember that it is a function of 2 variables now, x and m, and you can take the limit. X is what? R by r star, m is cos theta, x equal to radius of the sphere divided by the size of the critical cluster, r star being the equilibrium size in its pure bulk state. That is the way to understand. So, with did I say equilibrium size? Yeah, critical size in the bulk state. If you put x equal to 0, it goes back to homogeneous nucleation. X equal to 0 is x equal to 0 is like a case where R star is very small. Yeah, it's like a point particle. So, particle does not exist. R star is very large, yes. So, point particle. So, there is no particle at all. So, it is like a homogeneous case, and you can see that when x equal to 0, it just becomes 1, I guess, everywhere. So, that is fine. But the other limit is difficult to take, x equal to infinity. I have done it once. It takes a lot of Taylor expansions up to the third order or something, then only they start. Otherwise, 0 by zeros you get to make sure that it does not become, you get a finite. So, you can use L Hospital's rule and all that. And I think in the original paper there was a mistake. I have corrected it myself in the previous time when I gave the lecture, but there is a factor too. I did not get time to check it this time, but this does go to the correct limit when x goes to infinity. It goes back to f of m, thereby corresponding to the flat surface case. That is the whole idea. So, that is what it does. We just go beyond that and see how the angle of contact, the interplay of m and s and the particle diameters come into picture. Here this graph shows the heterogeneous nucleation rates for a specific 2.2 micrometer particle as at different contact angles and varying supersaturations. So, the role of interplay of supersaturation and angle of contact is what you see here. So, for even at low supersaturations, if the angle of contact is smaller, you can see the rates going up very rapidly. You hold the, so take for example, S equal to 1.05, 5% supersaturation. As you bring down the contact angle, the rate goes from -11 to +23, or let us say plus 23 when angle changes from 20 to 10 degrees. Looks like a small change in theta, but a tremendous change.
But theta equal to 0, it is independent of supersaturation.
Yeah, but theta equal to 0 is obviously R star itself was 0, no? So, there is no, it will spontaneously, see R star was 0. So, spontaneously moment as more than 1 is there, it will nucleate. So, that is a pathological case.
But the number 10 per 33 is, but there is still a number.
Yeah, but these are two ideal calculations. So, he just ran a program and I got this. It follows from that e to the power minus kind of a graph. Just applied the delta G by kT reduction, that is the idea. In reality, 10 to the power 16, 17 per cc are often seen and done. I remember the experiments, which is like 10 to the power 23 or so per meter cube per second is the kind of number that one sees in a burst nucleation phenomena. Yeah. So, basically to summarize, heterogeneous nucleation on foreign bodies like aerosols is a very complex process. We have captured only the minimum essence of that whole phenomena. It is vastly relevant in all models of the atmospheric for particle formation, and it is even very important in theories dealing with the nanoparticle synthesis engineering, particle engineering also, because we use similar concepts to find out how many new particles are formed from my catalytic vapor, from my precursor vapor. I just thought we will spend few minutes on rehearsing or recapitulating what we did. Many of the questions may be repetition, so you need not worry. It is just to keep our mind tuned to the topic that we are discussing. So, why the evaporation rate formula? I did not discuss evaporation rate formula, so ignore it. We will do it at some other time. Zeldovich factor, anybody among the four of you? What was Zeldovich factor? I know you know that. Whether people remember they have heard something. So, Anybody? Manjot?
No return probability.
Huh?
No return probability.
Right. Remember, that much is a curvature dependent probability of passing on further or not returning back. So that's right. So question 4, ethanol has 3 times lowest surface tension. Earlier, if you remember, we made a table for some 6 liquids. We gave its surface tension, delta G by kT, all this critical number of all the critical number, etc., etc. But interestingly, you see that its surface tension is 3 times lower and barrier height is 3 times larger. So now you tell between water and ethanol which one will have higher nucleation rate at specified S. Because you have a sigma term in the prefactor, if you see. If you go to the nucleation rate formula, there will be sigma has a major role to play. So you have to basically balance it out and see which one dominates. That's the whole point. Correct? If you go to the nucleation rate formula, it has a one is prefactor, but even on the exponential, that NC also has a sigma there. Correct? It is NC by ln S whole square. So I am not sure if I have a unique answer to that, but this is just to alert you that one cannot easily make a statement from that. You have to really balance e to the power minus delta G by kT formula. It is a Zeldovich factor, and here this formula where we must see NC here also has sigma G by kT, sigma cube is there. Now S, I said, has been brought down by some factor in the problem. So log S change is in the denominator, NC is in the numerator. So there is a bit complex effect. It is interesting to work out and see whether between ethanol and water which is likely to nucleate faster. Yeah. And problem 5 is a very practical problem. It's something which people as engineers should be able to think and answer. So air at 70% RH at the normal 30 degrees is quickly cooled to 10 degrees. Now you should be able to argue whether that will be a supersaturated system or not at that. So what should be that is the problem. What will be the degree of supersaturation achieved, and what should be the original RH to have S equal to 1. That is the idea. So at what humidity of 30 degrees, when you cool to 10 degrees, it becomes just S equal to 1. It is an interesting mapping you can do to find out why cooling creates a supersaturation and how much cooling I have to introduce for my, it is an AC air conditioner problem basically, how much cooling I have to introduce to remove out my water vapor. Yeah. Other things I think are simple. Yeah, how will the homogeneous nucleation rate, last question, how that will be affected by the presence of foreign particles now in the atmosphere? Homogeneous, I have a homogeneous case and I have foreign particles. Now, will the homogeneous nucleation sustainable if I have foreign particles? And I start with a given supersaturation, S value may be large, S equal to 6 I start. So it's a tricky question. So anybody, any thought? Anybody?
Chemical potential is not affected. Tension is also not affected for homogeneous.
Yeah. Yes. Theoretically it should not, but then what happens is it doesn't get even initiated because condensation on existing particles is so overwhelming that even before the because nucleation is also takes some time. we have discussed steady state, but it takes some time to start the process, maybe microsecond. But if you have a large number of foreign bodies, my vapor pressure comes down much faster, even before the beginning of my homogeneous nucleation. So, typically it is extremely difficult to maintain homogeneous nucleation, or in aerosol a practical problem called a new particles formation if the old fellows are not removed. So, all these particle reactor technologies have to quickly remove out the preformed particles to get new particles out of the vapor. So, that is how it reflects in atmosphere also. So, having foreign particles often is tantamount to suppressing homogeneous nucleation. I have maybe 5 minutes, I will just introduce, but we have very little time. One more topic, we must be having 3 more lectures, I think, 3 or 4 I think from now. So, we intend to cover the problem of hygroscopic particles, then the question of condensation rate and evaporation rates. In the next lecture I wish to complete it, and in the remaining 1 or 2 lectures, maybe 2 lectures, we will try to address some electrical effects, aerosols and electric, because most important part in atmospheric aerosols for technological perspective is their charge and how they are charged and how they behave and how do you design instruments and all that. So, we will try to spend some time on electrical concepts. Yeah. So, hygroscopicity is another property that influences the growth of or formation, in some sense formation of particles or its growth. Just as the heterogeneous effect was, it made particles which were invisible earlier, they become visible in your instrument. So, you can treat it as formation of new particles insofar as your instrument was concerned. Same way here also hygroscopicity is a tendency to grow by virtue of increased attraction between the vapor and the molecules. However, the theory is not the same as the heterogeneous nucleation. You have to invoke very different, this is where the contribution of Kohler and all came, and it very much depends on the very elementary theory itself does not depend on so much on the free energy kind of consideration. Free energy of course is always there, but it comes from things like Raoult's law, for example, very colligative model for change in vapor pressure. Yeah, free energy will be there, but you do not need to go into minimization of free energy or critical nucleus as a concept, because we are not talking, my vapor is the same. So, it is a foreign body whose property has changed. So, we do not discuss a condensation on my foreign body because my foreign body itself undergoes dissolution in the very liquid. In all the previous studies, my foreign body was totally insoluble, surface remained intact, which is no longer true.
So it's not just wetting angle.
Wetting itself, yeah,
Because theta I would have assumed is very low for
exactly. It is more like a wetting, highly wetting system, wetting, because it dissolves completely.
different form of film also you will.
Yeah, moment a form is film, the solid dissolves, becomes a part of the things. So, it becomes an equivalent of effectively a solution, thermodynamics.
So are we saying that for example, if we put salt, the vapor actually is absorbed by the salt, and then the vapor dissolves the state of water. State
Precisely.
of water is vapor, right?
Exactly.
Which gets absorbed.
Yes. So, transition is from a solid to a solution, but equilibrium dynamics when you do, you see the difference between a pure solution and a system of a solid and this, and that is how the theory is done. And so, we derive what is called as a Kohler's theory, which is simple theory, but very illustrative and dramatic implications. So, that we take up in the next lecture. Yeah, thank you.